All right, everybody, welcome back. We're going to take our notes and learn about 11.4 planes in space. 3 objectives in this lesson that we're going to have. One is going to be to find equations of planes. Now that we have completed the cross product, we can now find equations of planes. We're going to compute the angle between planes, in which we already know the formula because it's not going to be any different than what we did in 2 dimensions as it is for 3. And lastly, determine if planes are parallel, orthogonal, or neither. Same process that we did in 2 dimensions when we were talking about vectors. All right, first up, the equation of a plane is going to be given to us in the form of ax plus by plus cz plus d equal to 0, where they're telling us that this magical d value is some distance from the origin, but you got to take d divided by magnitude of u. Now, we'll show that, but it's not going to be as necessary for the purposes of this unit. Okay. Next, how do we determine a plane in 3 dimensions? Well, a plane in 3D is determined by a point and a vector orthogonal to the plane. If we go back to 2 dimensions and we were writing equations of lines, what would we need? We would need a point and a slope. This is going to be very similar. We're going to combine, compare, contrast all of this, and it's very much going to line up because the point in 2D for a line is the same as the point in 2D for a plane. In 2D, the slope is going to be like our vector. And this vector that we're going to be working with that acts like the slope is said to be orthogonal to the plane. And we know orthogonal means perpendicular, so it's going to be perpendicular to the plane. So I'm going to use these a few times throughout this lesson. I've got some big old flat dry erase board backside here. And we talk about orthogonal to the plane. What we're going to be talking about is some vector that is perpendicular to it at some point. Whether it's at the top or the bottom in the middle, it's going to be perpendicular. So if I turn it this way, you can see that this point, this pen, is going to be perpendicular. Okay? Now, that's what it means to be orthogonal to the plane. Well, who wants to say orthogonal to the plane, orthogonal to the plane, orthogonal to the plane all day? So just like you've seen in this unit with vectors, mathematicians came up with some notation, some terminology, and that's what we have here. This vector orthogonal to the plane is called, has the name, a normal vector. And it's going to act like the direction vector. It's going to act like the slope, okay? Although when I lift up the board and I bring it back here, it's not actually in the plane. It's perpendicular to it, orthogonal. But that's what's going to help with our direction, okay? Now, nice for us is that this normal vector is listed with the A, the B, and the C. They're the components of the normal vector. They're like the rise over the run, the slope. And you can see in the equation that they are in front of the X, the B, and the C. Very similar to our I, J, K in that order. Okay? So how are we going to do this? How are we going to write the equation of a plane, just like we would write the equation of a line? Well, we need 2 things. We're going to need a point and the normal vector. A point and the normal vector. They will almost always give us the point. They may or may not give us the normal vector. They may flat out tell us. They may tell us some other information. Or they might just give us a whole bunch of points, at which, because we've learned the cross product, we can compute the normal vector. Okay? So I think if we start going through some examples, we're going to see how this works out. So let's take example number 4. Slide the screen to right here. Let's take a look at example 4. Write the equation of a plane that contains the point, notice the parentheses, the point, negative 5, 1, 0, and is parallel to that plane. Okay? What that's telling us is that we're going to have 2 planes, flat surfaces that go on forever. Now, clearly, I can't make them go on forever, but I got these 2 nice boards, and what we want them to do is be parallel. However we do it, we want them to stay parallel. Well, if they're going to be parallel, then doesn't that mean that if we were in 2 dimensions, their slopes would be the same? But since we're in 3 dimensions, we're talking about a plane, that means that the normal vector must be the same, right? Because it's got to go to both of them. So if I'm looking at this problem and they give us, find the equation, the plane parallel to this, first thing we want to do is pull out of here the normal vector. So in our case, the normal vector is 2, negative 7, and 13. Now, you're asking, well, what about the -4? Well, we don't need that, because if we were doing parallel lines, switch colors over here, and let's make a note. Parallel lines in 2 dimensions, y equals, I'm making something up here, 3/2 x minus 1, and y equals 3/2 x plus 8. Notice the -1 and the 8 are different. That's what's going to change when we do a parallel plane. The d value, the magical d value, is going to change. So we need 2 things. We need the normal vector and we need the point. And we can see right here that the point that they're giving us is -5, 1, and 0. We have everything we need. Everything we need. So let's go ahead and start by writing the equation and find a new d value. So we're going to take 2x minus 7y plus the 13z. We're going to remove the -4 because that's what's going to change, just like the -1 and the 8 in my parallel line examples. And we're just going to go plus d equal to 0. Okay? Let's put this in a box, move it over a little bit like so. There we are. Now, we need a different d value. So we plug in the point just like we would the point slope form. Plug in the slope, plug in the point, simplify. Okay? So 2, switch that to blue. 2, take out the x and let's put in the -5. Minus 7, take out the y, put in the 1. And lastly, take the 13 and we're going to replace that z with a 0 plus d equal to 0. So -10, -7 plus 0 plus d equal to 0. Looks like we have a -17 plus d equals 0. Remember, we have to get d by itself here. Okay, so we have to actually subtract or add it over. Don't just stop short. There's our 17, so d is 17. So now we have to rewrite our equation that is parallel, and we do that with the 2x minus 7y plus 13z plus, in our case, 17 equal to 0. And now we have a plane parallel to the original one that was given to us. Notice the 2, the -7, and the 13, the normal vector numbers are still present. But we have a different d value, just like we do in the green parallel lines example, a different b value. Okay? All right, so that's example 4. Write an equation of a plane. Let's look at another one. So here, in number 5, they're saying write the equation of the plane that contains the point -1, 4, 2 with the given normal vector. So they're telling us the normal vector. We don't have to pull it out of the equation. They're telling it to us. So we can go ahead and start with our plane equation just like we did in the previous one. 3x minus 2y plus 1z plus some magical d value equal to 0. We need to know what the d is. Let's plug in the point. 3, -1, -2, multiplied by 4, plus 1. And clearly I don't have to write the 1. I'm just trying to keep it nice and organized. Plus d equal to 0. -3 minus 8 plus 2 plus d equal to 0. -9 plus d equals 0. D is equal to 9. So then we can write our answer. Let's tuck it over here. 3x minus 2y plus z. At this point, I'm not going to write the 1. Plus 9 equal to 0. Now, it is possible that you might see the answer written with the d value on the other side, where they've actually subtracted or added it over. It is possible you could see an answer show up that way. Okay? All right. Let's step up our game here with example 6. Same question, different presentation. Here what they're doing is they are giving us 3 points. Well, we can't do anything with this straight away because in order to do that, we need vectors. So before we can even do anything, we have to make these points turn into vectors. So what we're going to do is we are going to name them P, Q, and R. Sometimes we might name them A, B, and C. but since they're already given to us at PQR, that's what we're going to do. Now, I can't plot these in 3D, but you could go back and watch the video that I posted about plotting points in 3D if you'd like. But you don't need that. What we need to know and understand is that, hey, when we find this normal vector that we're going to find, they have to cross at the same point. And I'll show a demonstration of that momentarily. But first, let's make some vectors. Let's make the PQ vector first. And we know that we're going to make vectors by doing subtraction, terminal minus initial. So -2 minus 2 for a -4, 6 minus 0 for a 6, and 2 minus a -4 for a 6. Okay? Next, I want you to do the PR vector. Okay, PR. You're wondering why? Well, I'm going to tell you why in a second. Let's get the PR vector. So 4 minus 2 for a 2, 2 minus 0 for a 2, and -2 minus a -2 for a 2. Well, that's pretty convenient. We got 2, 2, 2 all the way around. Now, why did I have you do PQ and PR? Because what's happening is that these two vectors we've created, okay, two gray smartboard writing styluses, are intersecting. These are intersecting. They could be making a right angle. However, they could be angled in some way, shape, or form. I don't know. I didn't plot them. But I know they're intersecting. And the place where they're intersecting, right here, is point P, down here at point P. Because what we're going to be doing next is we have to create the three-dimensional piece in which we create a vector that's going to be perpendicular to both, and they have to do that at the same point. So that's why we're going to be using P. Because remember, from the good old days in geometry, two intersecting lines, they determine a plane. Like if I bring the board back up here, like so, and I put the two lines on here and kind of hold them, you can kind of see right here that, hey, they're on a flat surface called a plane. And they're intersecting at some point, which we're going to call for now P. So now at this point, we've got vectors, but we still don't have what we need, right? Okay, so if you think about this, we need 1, a point, and 2, the normal vector. And since a normal vector by definition is orthogonal to the plane, and we know from the previous lesson in 11.3 that you create vectors perpendicular orthogonal to the plane with the cross product, we're going to do the cross product with our vectors. So we are going to do the cross product procedure with our vectors. Okay? So if we go in order here, think about this. We did that first. Then we asked ourselves what we needed second. Now we're going to come over here in third. We're going to do the I, the J, and the K with our vectors, not the points. -4, 6, and 6, 2, 2, and 2. Show our determinant bars like so. The I will be made with the 6, 6, 2, and 2. Minus J, remember the middle one is always subtracted, with the determinant bar -4, 6, 2, and 2, plus K multiplied by the -4, the 6, a 2, and a 2. So we're going to do our computations. 12 minus 12 is 0, so we have a 0I here. Don't forget to bring the I down. Okay, this one's going to be -8 minus 12. Remember, we're doing AD minus BC for a -20. Now, remember, you've got a -J. This often gets forgotten. And we've got a positive 20J when it's all said and done. The last one, -8 minus 12 for a -20. There's our K, so a minus 20K. So what we've done is we have now created a vector orthogonal to the plane that contains the previous two vectors. So now what we can do is we can go ahead, put it in component form at 0, 20, and -20. And now if you look at what we needed here, we need the normal vector and we need a point. But we have to think about which point should we use. Well, since we used P as the initial in both of them, we now want to go up here and use point P. Okay? So, in our order of events, then we can go and start to make our plane with 0x plus 20y minus 20z plus the magical d value equal to 0. We can now substitute in our point, and we have to pick the point we use for both of them. So 0 multiplied by 0 plus 20 multiplied by, whoa, back up, Noble. I was looking at the wrong place. How about 0 multiplied by the 2 plus 20 multiplied by the 0 minus the 20 multiplied by the negative 4 plus d equal to 0. Well, is this really going to happen where we're going to have not much of anything here? Okay. So it looks like we're going to get 0, 0, 80 plus d equal to 0. Extend, subtract off the 80, and d is negative 80. So we can write our final answer, and I'll write it both ways, and then we'll show this. 0x plus 20y minus 20z minus 80 equal to 0. Now, clearly you wouldn't see that in the back. They would never write the 0x. So then at this point, we would probably make it 20y minus 20z minus 80 equal to 0. This would be what I'm looking for. But I will say, you could also see this. Y minus z minus 4 equal to 0. You could see that. Because if they're all divisible by 20, I could easily divide them all by 20. Okay? So, that is how you write the equation of a plane given 3 points. Okay? Let's turn this over to the next page. And let's look at angles between planes. Angles between planes. If I give you two plane equations like you see here, I want you to find the angle. Now, clearly, they've already moved the 1 over to the right-hand side. That's the d value. But it's not necessary for our work. Because what we need to know is how the normal vectors are relating. So if we think about this, we have normal vector number 1 of 1, negative 2, and 1 from the first equation. The second equation is a 2, a 1, and a 1. And those are the coefficients in front of the x, y, and the z. So remember, normal vectors, those numbers a, b, and c, are those vectors that are orthogonal to the plane. Well, how are they interacting? How are those normal vectors crossing is the question. Well, this is where we'll use our formula, cos theta, to make that determination. So let's say cos theta is equal to u dot v over magnitude of u times the magnitude of v. So cos theta equals 1 times 2 plus negative 2 times 1 plus 1 times 1 all over square root of 1 squared plus the negative 2 squared plus the 1 squared, second square root, 2 squared plus 1 squared plus 1 squared. Numerator looks like a 1. Denominator, what's that, a 1, a 4, a root 5. Second one, wait, how about a root 6? How about a root 6? I think I misadded there. Let's go with a root 6 and a root 6. Okay, bring down our cos theta. If you want to go straight to the calculator now, you can, but we could simplify this, right? Root 6 is actually 1 over 6. And now at this point, we want to find the angle between. Let's bring up the calculator. Slide it over. And now we can take second cos of 1 divided by 6, hit enter, and get 80.4 degrees as the angle between the normal vectors, which is the same as the angle between the planes. So theta equals 80.4 degrees. But you'll notice right there, to find angles between, we're using the same formula we used in the first part of this unit. Okay? All right. Next up, determine if planes are parallel, orthogonal, or neither. So that one in example 7, we found the angle. Here they're saying, hey, tell me if they're going to be parallel, orthogonal, or neither. Well, the parallel check is the same as it was for parallel or collinear in the first part of the unit. You're going to look for scalar multiples. Parallel, scalar multiples. Or if you're crazy and really want to do a little extra work, do the cross product. And if you do the cross product and you get 0, 0, 0, well, you know that they're going to be parallel. But I think you can look at them and make a determination just as quick. Orthogonal is the dot product. And if it's 0, you know they're going to be orthogonal. And then, if you don't get either of those, it's got to be neither, at which point I'm going to say, hey, go ahead and find the angle between them. Okay, best way to do it is do a problem, see how it works. Example 8, determine whether the planes are parallel, orthogonal, or neither. So first, let's check parallel. So we have a 3, a -2, and a 1, a 2, a 3, and a 4. So you look at the two normal vectors, because we don't need to worry about the d values, and you say, are they scalar multiples? So you can look at them as well as I can. 3 goes to 2, but -2 goes to 3. There's no one number that multiplies by any one of those. So this one is not scalar multiples. So not multiples. So not parallel. Okay? So then next question would be is, are they orthogonal? Let's check the dot product. So orthogonal, we're checking the dot product. 3 times 2 plus, you know what, let's back this up. Let's make a note here. Dot product equal 0 question mark. So 3 times 2 plus -2 times 3. That's a good sign. That's a good sign right there. Plus 4 times 1. Oh, that sign went away. We've got 4. So not orthogonal because dot product does not equal 0. Okay, therefore the answer is neither, but oh yeah, check the directions. If they're neither, find the angle between. Okay. Angle. Cos theta is equal to, we know that the numerator is the dot product, so let's just go ahead and take the number that we just found, 4, put that over, let's go 3 squared plus 2 squared plus 1 squared. Now you know that if I don't write the negative, it's okay, because anytime you square it, it becomes positive anyway, with a 2 squared, a 3 squared, and a 4 squared. So we have 4 over the square root of, what's that, 9. 4 makes 13, a 14. And the second one is a 4 with a 16 is a 20, a 29. A 14 and a 29. Okay, root 29 like so. Cos theta. Let's go get the calculator. And let's go ahead and compute it. Second cos 4 divided by open second root 1 4 right arrow second root 2 9 right arrow close it enter it, and we've got 78.5 degrees. 78.5 degrees. So theta equals 78.5 degrees. Okay. Two things that I can think about as we end this. If you ever come up with a number bigger than 100, or I'm sorry, bigger than 90, just take its supplement. That's what would be in the back of the book. They always look at the supplement because any way you do it, there's always going to be two angles, a complement and a supplement, one acute, one obtuse. So if you get an obtuse, do its supplement. That's first. Second, you might be sitting here thinking, well, Noble, what if I just went ahead on a question like this and just said, you know what? I'm going to just try to find the angle. Well, that would tell you right off the bat, right? That would tell you. Because as you do it, you'd find out your dot product, so you'd know right then and there if it came out to 90, and then you'll probably be able to recognize because of scalar multiples for parallels, so you could just go straight to the angle and probably save yourself some time. It's very possible. All right, so problems to work on from 11.4, do as many as you can, and then bring some questions back to class the next time we meet. All right, have a great day.